first, let's find dy. So you know the definition of the differential dy is f prime of x dx. So taking the derivative, I get 2/3 x to the negative 1/3 dx. And I'm always going to suggest that you put negative exponents in the denominator. Okay, so then dy, if I substitute in x equal 1, so that's just 1, and then dx is negative 0.01. And so then, well, that's just, yeah, it is what it is, right? Negative 0.02 over 3. So it's a small negative number. You can go figure that out on a calculator. This is a fine answer, but I want to make sure that you know how to sketch it. So what that means is we have to graph the x to the 2/3. So here it is. I'm going to draw the tangent line at x equal 1. So at x equal 1, here's the tangent line. And you have to really think about zooming in on this, right? So I'm going then the opposite direction. So this dx means I'm moving this direction by 0.01, right? So I'm just going to put it here. So negative 0.01. So between these two x values, that's what the dy is. So I go to that x value, and then from the x value of 1, that's already there, right? So let me get a different color here. So this here is dy, and it's negative because from here I went down. Good? Okay, let's try the next one. So now we want to approximate. So this is where we have to find the f of a plus dy. We have to do everything, right? So first we're creative, and we think of what is the function going to be. I'm pretty sure the function is going to be x cubed. And I'm thinking, what is the nice number a? That looks like 2. Then the dx is going to be 0.02. So then I'm going to go find the dy. So the dy, again, is f prime of x dx. So I get 3x squared dx. So I'm going to plug in the x is equal to 2 here. And then the dx is 0.02. So if I multiply that out, I get 0.24. Okay, doesn't say to graph it, so I'm not looking at that this time. What they want me to do is to approximate using the linearization. So the linearization at 2.02 is going to be f of a, and in our case, that f of a is going to be f of 2 plus my dy. F of 2 means I'm plugging 2 into my original function. So I get 8. And then plus my dy, there it is, 8.24. Let's do another one. Again, we have to think of what the function is going to be. So it's going to be sine of x. And then the a, the nice number, well, I'm looking at this and I'm thinking 60 degrees is close to 58 degrees, right? But we can't do degrees in calculus. We have to change that to radians. So that's pi over 3. So my a that I'm going to draw the tangent line at, or use for the differentials, is pi over 3. So then how do I get to 58 degrees from 60 degrees? My dx will have to be negative 2 degrees, but I need to change it to radians. So I multiply it by pi over 180. So dx is negative pi over 90. Okay, so I'm going to erase this and make some room here. Need to find the dy. So dy is the derivative cosine of x dx. Now I'm going to plug in my nice a value right there. Cosine of pi over 3. Dx is negative pi over 90. You can't leave it like this. You have to tell me that you know cosine of pi over 3 is 1/2. And then there's a negative pi over 90. So I can say my dy is negative pi over 40. Oh, sorry, not 45. Sorry about that. I'm doing incorrect math here. Negative pi over 180. Okay, so that's my dy. So how do I find the linearization at 58 degrees? So that's going to be f of a, so f of pi over 3 plus my dy. So f of pi over 3 means I put pi over 3 into my sine function. So that's root 3 over 2. And then plus my dy, I end up subtracting that. So that's a fine answer right there.